Thanks for having me here. I didn't know it was an 8-minute talk, so if it were 10 minutes, I would have given a talk on non-Hermitian physics.
It's 10 minutes if you want.
But I'll just give her physics.
10 minutes.
Okay, some physics. I'll talk about some physics. Okay, so what is this physics that I'm interested in? So you can see some videos running in the background, and this is a model of epithelial tissues called the vertex model. But this is not your bread and butter vertex model. This has been modified to mimic some experiments that I'm going to talk in a bit. But what is unique about this is that you can see there are some cells that are in orange that are oscillating, and then there are some cells in blue that are not really oscillating. And this is a unique form of dynamical heterogeneity that arises in real tissues. And when we explored this, it turned out that it happens because of spontaneously broken PT symmetry and the associated non-Hermitian physics. But unfortunately, I won't have time to talk about it today. I'll give you some overview of the physics of these unique phenomena. So this work has been done in collaboration with Medhavi Vishwakarma's group at IISc and my group, and these are the students who did it. And this question is part of this broader conversation on whether epithelial tissues undergo glass transition or not. And what we have shown is that if you take the canonical vertex model, which is on the left, under no condition it will give rise to glass transition, especially like if there is cell division, which increases the density of the cells. And this is kind of counterintuitive, but what we had shown is that if you add something called mechanochemical feedback between the mechanics and the chemistry of the cell, it basically gives rise to a solid tissue. And when you analyze the dynamics, it's actually a glassy dynamics. And this gave rise to a lot of the phenomenology that I'm going to talk about. And all of this started when Medhavi showed me this plot. So this is a snapshot from a real experimental system, MDCK cells. And this has been, the cells has been clustered according to their density or according to their actin concentration. And what you see over here, there are these pink cells which have high local cell density and also high actin concentration, and the blue ones which have low actin density as well as low local density. So what is unique about this, it's as if there is a phase transition or phase separation between the high density and the cell low density regime. And what is even more interesting is that if you look at the behavior of actin, they keep oscillating, and the oscillation period kind of correlates inversely with the density of the system, or rather, correlate with the density of the system. If you have high density, you have a very high period, so you're not really oscillating. And if you have low density, then you're actually oscillating quite fast. And we wanted to understand what is going on and how exactly this is happening. So we have a 2D system where we have recapitulated this, but it is kind of hard to understand there. So all I'm going to show you is a 1D realization of this, where we can actually study it analytically and provide some information to it. So what I'm showing you is actually a 1D ring of spring and bead network. These springs are overdamped. And this is nothing but the 1D vertex model. The vertex model is nothing but a spring model, okay, in 1D. But what is unique about this vertex model is that, as I have mentioned, there is feedback between the mechanics, which is dictated by, say, the properties, mechanical properties of the spring, its current length, its preferred length, L and L naught, and also the chemistry of the cell, which here we represent in terms of the dynamics of a protein called ERK or ERK, right here. So what is special about ERK is that even though its chemistry is quite complex, you can sort of boil it down to the fact that it's a Hopf oscillator. So you can actually represent it in terms of some Hopf oscillator. For example, we have done using Brusselator here, which is one of the most well-known Hopf oscillators. But it doesn't have to be Hopf oscillator as Brusselator. It can be any Hopf oscillator because of some underlying symmetry of the 1D system. And also, as we are going to show, if you're close enough to the Hopf bifurcation point, the details does not matter, okay? Next, we have a degrader, because ERK has a degrader inside the cell, and it is also another parameter through which we can control whether there is a Hopf bifurcation or not. And it has its own dynamics, as does the mechanics part of it. But what is unique about this 5 set of equations, which is already quite complex, is that there is a feedback between the mechanics and the chemistry, And this product alpha and times beta is the feedback strength of this system, okay? So now this is a really complicated set of equations. I don't expect you to know and learn anything just by looking at it. But we have done that, so I'm going to tell you the story as we have done it. So the first thing that we did was to make it a continuum version because that makes it easy. And to do that, you basically take L going to L of X. Okay, I have 2 minutes. So what that does, you can basically convert this into this form. And now you essentially get effectively a diffusion equation in length. And this is kind of unique because this is not something that you usually get. But when you do that, all of that, you start getting all of these phases at really strong mechanochemical feedback. You get traveling waves, which is where the mechanics dominates. At low enough feedback, you get what is called phase turbulence, where there is no traveling wave, but the phases are sort of randomly correlated with each other. But in between, you start getting some really unique. You start getting coexistence of region where there is no oscillations with regions where there is oscillation and phase turbulence. And what is special about this picture is that wherever you don't have any oscillation, that's where the cells are compressed. And wherever you have oscillation, that's where the cells are extended. This is very similar to the picture that I had shown you in the very first slide. And that gave us a lot of confidence that we are on the right track. So we wanted to understand what is going on over here. So we analyzed this transition. We found out that using something called kurtosis, and we found out that there were 3 unique points where there was really high kurtosis. The system was very intermittent. And we identified that with location of 3 dynamical phase transitions, okay? And they have certain properties that I'm planning to discuss later. But what is unique about the first DPT is that you go from this phase turbulent state to a state with oscillation depth, and it doesn't depend on the choice of the Hopf oscillator. It is quite general. For example, we have done this for Brasileiter. We have done it also for Fitzhugh-Nagumo model, which are very different models from each other. But the key is that you always get this transition. And that tells us that there's something general, something generic that is happening with all of this. And to do that, we went back to the fact that if you take this chemical D and vary its concentration, there is a point at which the system goes from an oscillating to a non-oscillating state, and that is the point of Hopf bifurcation, okay? And we are our system is right over here, so we expect the effect of the Hopf bifurcation to sort of affect the dynamics that we have over here. In particular, if we are right at the Hopf bifurcation point, if we look at the eigenvalue spectrum, there are 3 slow modes, 3 modes with 0 real eigenvalues, okay? And we can do something called the central manifold projection. Basically, you write down the hydrodynamic version of this. These are hydrodynamic variables. And when you do that, you can write down 2 coupled amplitude equations. So W is the complex amplitude of the Hopf mode, the oscillatory mode, and Z is the amplitude of the mechanical strain. I have 2 more minutes, right? Okay. So what is unique is that they are coupled, and if you look at it, so Z has a form that is similar to the Cahn-Hilliard form, okay? So we are not showing all the terms, but when you do that, it essentially have a Cahn-Hilliard form. What that tells you is that under some circumstances, as for example, when you increase the mechanochemical feedback, it spontaneously phase separates into a region with high strain and a very low strain, negative and positive strain. And wherever you have positive strain, you get oscillation. And whenever you have negative strain or compression, you have oscillation depth. And this does not depend on the property of the specific details of the Hopf oscillator. As long as you have a Hopf oscillator coupled with each other through mechanochemical feedback, you can recover that. So we basically took this theory out and then essentially said, like, what else can it predict? So one of the unique things that it predicted was that, so if you are right in this region where you are not supposed to get any oscillation, our theory predicts that if you increase the mechanochemical feedback, it will eventually give rise to this kind of coexistence between oscillation and oscillation depth, okay? And when we explored the region over there, we found that that is what exactly is happening. So whenever you don't have any mechanochemical feedback, there is no oscillation, but the moment you turn it on, you start getting a behavior like this. So that brings me to the conclusion. The first conclusion is that compression-driven oscillation depth is a generic dynamical phenomenon, blah, blah, blah. But the most subtle and something that we did not realize is that the conservation of the tissue length, because it is on a ring, it gives rise to an effective diffusive transport of the chemicals. Even though there is no diffusive transport, because of this mechanochemical feedback, you are getting effective diffusive transport. And that explains a lot of the model that people have used. There is no diffusive coupling, diffusive transport of, say, ERK between cell to cell, and yet people have used those models, have gotten right results. And our theory basically tells you why do the people get that. And with that, I thank you for your attention and happy to take more questions.
Thank you, Sumantra. Good questions?
There is a question.
Why did you use the word epithelial? What is epithelial?
What is special about it? Because the experiments were done on epithelial tissues. So epithelial tissues are all the tissues that are lining.
That means any tissue.
Yeah.
I mean, would this apply for any other tissue too?
Good question. So the thing is, we have experimental verification only for epithelial tissues. And the good thing about MDCK tissue is that it is essentially flat. So it is a two-dimensional system. So there is a one-to-one correspondence between theory and experiments. But we can generalize it to other tissues, of course, but then the geometry is so complex that we don't know how exactly to verify that. And geometry does play a role here.
You mentioned the system is tuned near the bifurcation point.
We haven't tuned it near the bifurcation. So the system is close to bifurcation, but it is not, it is actually, if you think about in terms of distance from, say, criticality or something, it is actually quite far. And yet, because of the mechanochemical feedback, it's actually bringing it closer to the critical point. Okay, it's a bit subtle, so we can discuss perhaps later.
Let's thank Sumantra for his talk.